So I want to welcome everybody again to tonight's webinar on research at our office. I'm Joe Deli Carpini, the Science and Operations Officer, and with me, two of our members of the science team in our office, Andrew Lecanto and Rob Megnia. One of my jobs is to manage our research program at the office, and I'm fortunate enough to have a lot of talented people like Andrew and Rob helping me out with a lot of the research and training that we do in the office. So we're going to talk a little bit about some of the research projects we're participating in right now and kind of, how they're going to be helping us improve our forecasts. So just to get started, why do we do research? We do forecasts and warnings that I'm sure you're very familiar with, but in the background, we also do a lot of different kinds of studies, not just limited to the case studies that we show you, but we want to always improve our forecasts and warnings, anticipating different types of significant events, whether it be blizzards, coastal flooding, hurricanes, severe weather, but also improve the ways we communicate the information to you. So think of things like social media posts, maybe new web pages that we have, different ways to display graphics as opposed to text. But we also want to bring new scientific techniques into operations from the research and university communities in particular. There's always new science that's evolving. So we want to bring that into our operations so we're not using kind of old, outdated procedures in our forecasting. And another good thing is we maintain relationships with those in the research community, particularly universities. And here in Massachusetts, we're blessed with a lot of universities in our area, also Rhode Island and Connecticut, who we collaborate with. And, we have a lot of student internships, which is great. We get some help on projects and give the students experience, but also leads to future employment. And a number of our former students are actually employed in the National Weather Service. We have one in Philadelphia, another one on the West Coast, Medford, Oregon, another one in Kansas City. So it's a nice pipeline to bring new employees kind of into the National Weather Service. So one of the programs we have is called Seastar, and this is kind of a national program through the National Weather Service. It's the Collaborative Science, Technology, and Applied Research Program. It brings our research into operations through collaborations with university, and most notably, University at Albany, which was formerly known as State University of New York, SUNY at Albany, and also NC State are kind of the most active here in the eastern U.S. They engage students in different applied research projects and work with NWS forecasters, and the projects are funded generally for 1 to 3 years and must address some of our science priorities. So it gives the students some kind of real-world research experience, and the results are often implemented into operations. So I'm going to let Andrew get started. We have a few different Seastar projects, some severe weather, some winter weather. So Andrew, I will let you lead it off.
All right, thank you, Joe. And so the first Seastar, actually, Joe mentioned about the Seastar projects, and one of the first ones, or the first little research that we are involved in, is this study on the severe thunderstorm evolution in complex terrain. What we mean by complex terrain is basically we have a lot of relief. We have valleys and hills sort of nearby, and that tends to affect the severe weather environment. So it's sort of good to know, have that sort of understanding of that sort of environment as it pertains to severe weather. So sort of a motivation for this project, back in August of 2019 was actually a really unusually active period of severe weather for the Northeast. 11 days of reported tornadoes, hail or damaging winds, and there were over 260 reports of severe weather reports in New York State compared to a typical August, which is averages around 76 reports. So a really active August, in August 2019. And the other thing that sort of characterized a number of these events is that they had a weak synoptic scale lift, weak vertical wind shear, and moderate to high instability. So that sort of characterized a number of these events. And there was a study done by Vaughn and co-authors back in 2017. Basically what they did was they looked at how well predictable are certain thunderstorm environments, and that's the little graphic that you see on the far left. The acronyms there, HSLC, that stands for high shear and low cape. HSHC is high shear and high cape. LSLC is low shear and low cape. And on the bottom right is low shear and high cape. And what we found that basically what the color code, the dotted color codes, basically describe sort of how, if the forecasts were, if they were well forecasted severe events or if they were poorly forecasted events. And for a number of these sort of low shear, high cape events, the majority of them were not well forecast at all. And statistically, the best are actually the high shear, low cape ones. So now we'll move on to sort of a case study of one event that occurred back in August of 2019. This happened in August 21st. And so pictured here are the severe weather reports across the United States, and then sort of zooming in on the far right, it just includes western New England, including the Hudson Valley. And you'll see a number of the severe weather reports actually sort of aligned in the Hudson Valley, where there is sort of the terrain there between the Berkshires and the Catskill Mountains in the eastern New York State. Now, sort of delving a little more into this event, what we call the cold pool evolution of this particular event. What we mean by that is when you have organized sort of lines of severe weather, what they can do is they can produce this sort of rain-cooled air behind it called the cold pool. And that sort of helps to sort of organize the storms themselves and help to sort of facilitate sort of new storms as they develop south and west of this cold pool. So what we see here is initially discrete cells start to move into the Hudson Valley. That's pictured in the left graphic there, and sort of you have the Catskills are pictured in the left, and that little black line there, and then sort of the Berkshires are sort of in the sort of pictured just in the far right there. It's sort of in between is the Hudson Valley. And you have all these sort of small little cells that sort of had developed and moved into the Hudson Valley here. And then as we move through time here, the storm started to intensify, and then the individual sort of cold pools, what they did was in the second, sort of the middle graphic there, shaded there is the temperature. And what you'll find is that basically those cells started to their individual cold pools basically combined into one. And that was sort of important because as we move on to the next slide, what we find is that the storms will basically sort of align along that sort of cold pool and sort of redevelop, and actually eventually as we move forward in time, we actually will just look to see, and actually what they did was actually they trained along this gust front, and that sort of led to some significant rainfall as well, besides the severe weather. So that was sort of a really critical aspect of this particular sort of event here. And just as we move on to the next slide, the new cells, again, they initiate along the western end of the gust front. And then the cells, again, as we mentioned, they sort of trained along it as they sort of matured. So not only did they produce severe weather, but they also produce a decent amount of rain, as we'll see in the next slide. You see locally amounts exceeded sort of 1.75 inches of rain, which is a decent slug of rain overall. And that, that kind of rain can lead to localized flooding as well. We didn't have too many reports of that at this point, but this kind of rain certainly was significant. And just moving on, just discussing sort of the current and future work specific to this project. The study cases, they date back to 2016 to compile area averages of surface variables in the Hudson Valley, basically to try to come up with just some tips to try to predict better severe weather forecasting, identifying cases with back building through radar analysis, and then also to sort of expand the study area to include the Connecticut River Valley, sort of more into sort of our forecast area of responsibility in western Massachusetts and into Hartford County in New York and in Connecticut. And then also we'll use it to sort of create maps of severe weather indices that we can use to, again, to try to better predict severe weather environments in complex terrain. All right, and with that, what I'll do is I'll pass the baton over to Rob. He's going to talk about the next two research cases here.
All right, thank you, Andrew. So give me just a second while I expand my screen here. So this was a project that was done as part of the Seastar program that Andrew mentioned with the University of Albany in NWS Albany and NWS New York City as well. And the goal was to improve tornado detection and lead time. So this was an update on a study back in 2017. And again, the goal is to try to improve our understanding of the synoptic and mesoscale environments that lead to southern New England tornadoes. And also it looked at different radar signatures that we can look at in real time that may be able to tilt the odds in our favor to make good decision making when we're considering the potential for a tornado warning. And actually, a detection scale was developed to give us a tool, to give forecasters a tool with warning decisions in real time. And this also builds on an earlier study from Brooke and co-authors back in 2008 that classified different synoptic height patterns for tornado events. So they gathered tornado events between 1995 and 2006. And they broke the synoptic patterns for these tornado events into 5 different categories, types A through E, with type A being a closed low being situated over Ontario, type B being an open trough over the western Great Lakes, type C being a deep trough over the eastern United States, and then also with types D and E, either a tropical cyclone remnant or a cold pool aloft. And then after looking at some of the patterns that lead to tornadoes, they developed a basic radar warning strategy. So here's just to give you a visualization of some of the different classifications of height patterns that I mentioned on the last slide. So on the left, we have type A, which is the most common setup, where you have the closed low kind of situated over Ontario. And then type B, which made up 1/3 of the events that the tornado events that they gathered, is defined by that kind of open wave trough over the Great Lakes. And then here on the next slide, we have, for examples, type C and E, which only made up 3 of the events in the database. But again, type C having that deep trough situated over the eastern United States, and type E with the cold pool aloft. So here's a look at some of the parameters that they looked at for the environments associated with the tornadoes. And these are some of the parameters that we look at to determine whether or not tornado development may be likely when there's a thunderstorm present. So on the horizontal or the x-axis, we have instability represented by CAPE, which is convective available potential energy. And on the left, on the vertical axis, we have storm relative helicity, which is kind of a measure of low-level wind shear. And these 2 parameters combined kind of give us an idea of when thunderstorms might have rotating updrafts. And that's what we're going to need for tornadoes to develop. So as you can see, for almost all of the events kind of represented by the blue dots, you see that the 0 to 3 kilometer helicity is almost always above 100. So that can be a good discriminator for some events. And in general, you're going to have some instability greater than 500 units of CAPE. So another thing you need besides instability and shear for tornadoes and thunderstorms is you need moisture, right? You're not going to have any thunderstorms without moisture. So that was another thing they looked at, and they found that dew points average anywhere between 68 to 73 degrees Fahrenheit at the surface. And in addition, they also looked at precipitable water, which is kind of a measure of moisture vertically through the entire atmosphere as opposed to just dew point at the surface. And they found that the precipitable water usually average anywhere between 1.5 inches to 2 inches, and with a cold pool present, values could be 1 inch or less when dew points were between 50 and 60 degrees Fahrenheit. So kind of after looking at those different parameters and the different synoptic environments that can lead to tornadoes, they decided to look at past cases on radar and see if there was a way they could develop some kind of tool that could tilt the odds in our favor when making decision making when we're active in real time and watching these tornadoes. So kind of on the top left in this table, we have two parameters that we can see when we're viewing the radar and when we're in warning operations. So on the far left, we have rotational velocity. And the second column is a parameter called NROT, which stands for normalized rotation. So this tornado detection scale, what it does is it kind of adds up a score based on values of rotational velocity or normalized rotation. And then based on that score, they were able to determine whether or not a tornado is likely. And in addition to the radar parameters, in the bottom left, we have these corrections where you may add or subtract points for other scenarios. For example, like we talked about earlier, you need a good, strong, low-level helicity in order for tornadoes to occur. So if you have 0 to 1 kilometer storm relative helicity greater than 100, add 1 to that. And we also know that we need a lot of moisture, so we can add a point for precipitable water greater than 2 inches. But generally for tornadoes, we want to see the LCL, which is the lifted condensation level. We want to see that higher than 1,000 meters, so you might subtract a point if the LCLs were a little high. And also for classic supercell structure cases, they were subtracting 2 points as well. So pretty much anything under a 5 was determined that a tornado would be unlikely. 6 to 9, a tornado was possible. And when you got to the 10 to 12 range, you started getting an increased likelihood that what you're seeing on radar could be a tornado. So based on that, they were able to develop a strategy. You know, if applicable when you have a score of 5 or 0, you might just issue a severe thunderstorm warning, but tag it with a tornado possible. And, you know, otherwise, when you start getting to the 6 to 8, 6 to 8 is when you would add the tornado possible tag. And then when you start to get to 9+, when you're issuing the tornado warnings, there was a good amount of success with this detection scale. And that was actually put to the test back in 2018 and 2019. And this scale was able to help with forecasters issuing warnings, making quick decisions. And I was able to get warnings out for the Cape Cod tornadoes in 2019 and the Dudley Webster tornado in 2018 with greater than 20 minutes of lead times. And furthermore, they went back and looked at false alarm cases, which is when we issue a tornado warning and then nothing happens. And they found that in 10 of those cases, the tornado detection scale did not exceed 9. So that 9 points they came up with can be a pretty good discriminator. And if used, that could potentially help us lower our false alarm rate. So now we're going to shift gears a little bit and start talking a little bit about hydro. So we also have a Seastar project that's being done with NWS Caribou and NWS Gray, which are both offices up in Maine. And this is to assess warm season model precipitation in New England and to try to identify situations where warm season model precipitation coverage, location, and maximum amounts are skillful. Because frequently the extent of heavy precipitation can be too great and can result in an overestimation of flooding. So again, still on the hydro subject, we have the Flash Flood Improvement Project, and I'm doing some work on this with some other folks in the National Weather Service, and there's some research being done with the NWS in New York City and the National Weather Service in Philadelphia / Mount Holly. And this is also a part of a larger project involving many other Eastern region offices. So kind of the goal of the project is to incorporate Flash into operations. And I'm going to tell you guys a little bit about Flash in the next slide, but basically it's just a suite of products that we use for situational awareness in extreme precipitation situations. And we're also trying to be able to use sub-hourly radar rainfall rates in improving our flash flood warnings, as well as to determine favorable synoptic and mesoscale environments, similar to, like I discussed with the previous project with the tornado environments. We can do the same thing for flash flooding to get an idea of when we might be able to expect it. and also trying to come up with a standardized verification score. So you heard me mention FLASH on the last slide. So FLASH stands for Flooded Locations in Simulated Hydrographs. And I also mentioned that it's a suite of hydro products at flash flood scale that we have in real time across the conterminous United States. We're getting this data up to every 2 minutes. So it can be really beneficial for situational awareness, especially, of course, during extreme rainfall events. So some of the products that we use in FLASH, kind of the three main ones when we're in flash flooding operations. The one I like to look at that's pretty popular is unit streamflow, which is a measure of runoff. So when you start to get heavy precipitation, at first a lot of it starts getting absorbed by the ground, but eventually the ground begins to become saturated. And when that happens, the water can't go on the ground anymore, so where does it go? Well, it just goes downstream. It goes towards its lowest point, and that's what runoff is. And when we start to see larger values of runoff, that's when we know we could be starting to see some pooling of water and maybe a hint that flash flooding may be beginning to occur. So in addition to that, we have average return interval, which we often use the ARI as a kind of an abbreviation. And what ARI is, it basically gives you an idea of how, when you're kind of looking at how much rainfall has fallen, how often does this amount of rainfall occur at this location over this amount of time? And usually we're looking at 1 hour precipitation, 3 hour precipitation, or 6 hour precipitation. And what FLASH may be telling us is that for a particular location, this amount of rainfall falls in 3 hours once every 10 years or once every 100 years. And once you start getting those really high average return intervals, you're getting the indication that, hey, this is an event that's out of the ordinary, so probably flash flooding could be occurring. And then finally, we have QPE to FFG ratio or difference. So QPE stands for quantitative precipitation estimate, which we often get from radar. And FFG stands for flash flood guidance. And flash flood guidance is actually determined by our river forecast centers. And they kind of determine, this is how much rainfall you're going to need over a specified period of time for a likelihood of flash flooding to begin. And similar to ARI, they're using flash flood guidance at 1, 3, and 6 hour intervals. So when the ratio of rain that has fallen begins to exceed the flash flood guidance, that's another indicator that flash flooding may be occurring. And that's another tool that FLASH provides. So another way we want to improve our warnings is by using impact-based tags. And the reason we do this is because, just like any other warning, like a severe thunderstorm warning or a tornado warning, there's going to be false alarms. There's going to be times where severe thunderstorms are more severe than perhaps other severe thunderstorms. There's big tornadoes and there's little tornadoes. It's the same thing with flash flooding. Sometimes you can have minor or basic flash flooding. Other times you can have considerable or catastrophic flooding, where cars may be being stalled or people might be being rescued or water is getting into people's homes. So the goal of impact-based tags is to try and distinguish between different types of events so that, when you get that alert on your phone for a flash flood warning and you see that considerable or catastrophic tag, it's not just your basic flash flood warning and that you may need to take action. But one big challenge, especially for flash flooding, is that we don't always know when to use the impact-based tags. I mean, we have our flash and we have our radar estimates, but there isn't a lot of research out there that tells us when we should be using those tags just based on data. A lot of the times when we're issuing these tags, it's because we're starting to get reports. And here's an example of some of, what might be a considerable report. Traffic cam image shows cars submerged in flooded underpass on an interstate. That could be considerable. And for catastrophic, when we're getting reports of waters in homes and water rescues ongoing, that's when we might already have a flash flood warning out, but then we get that information and we'll go back into the warning and we'll tag it as considerable or catastrophic. But what if there was a way that we knew ahead of time without receiving these reports? What if we could look at the flash data and determine, we might need to tag this flash flood warning as considerable or catastrophic? So what we're doing is we're gathering these local storm reports that we get for flash floods, and we're classifying them as either basic, considerable, or catastrophic. And then we go back and look at the flash data from the location of the local storm report, and then we try to determine, is there a pattern between the data we're seeing on flash and the local storm report severity of basic, considerable, or catastrophic? So maybe that way we can get an idea of what numbers we might need to look for to start using these impact-based tags. So at this point, it's early in the research, but there's been pretty distinguishable differences in values of flash, particularly with unit stream flow, that can distinguish between considerable flash flooding and catastrophic flash flooding. But we need further research to determine the difference between basic and considerable events, as when we looked at those, the flash data was actually pretty similar, with the considerable actually slightly higher, which is a good sign. But there's some promise for helping those impact-based warnings by using flash. So now I think I'm going to be turning this back over to Joe, and Joe's going to talk to you guys about forecast track biases in East Coast winter storms.
All right, thanks, Rob. And now we'll get into a little bit of winter weather. This is another Seastar project that we're involved in with University of Albany and National Weather Service in Albany and Gray, Maine. This is looking at track biases in East Coast winter storms. You're probably saying, what does that mean? Well, so we often have a rule of thumb in operational forecasting, and if you follow winter storms at home, you may have kind of noticed this. It always seems like the forecast position of a winter storm starts to trend west as we get closer to the event. So in other words, decreasing lead time. So in other words, a 3-day forecast might have the low well out to sea. It's kind of a miss. Oh, and everyone's snow lovers disappointed. Then, the 2-day forecast, now it's trending a little closer. Okay, maybe. And then, finally the storm really tracks close enough to give us either a big hit or maybe the interior of New England a big hit. But always seems, and we've mentioned this in the office too, it always seems like the storms will trend west with time. So this project is just looking at essentially the GFS model. Does it really have that kind of a bias, starting offshore all the time and then eventually trending west, to where initially we're thinking we're all clear or maybe a minimal impact, and all of a sudden we're right in the in the crosshairs of the storm. So this project started off looking at a bunch of different cyclone track, low pressure tracks over a number of years, and you can see them all kind of in the spaghetti plot here. And there's a lot of them, some coming across the Great Lakes, some coming from the lower Mississippi Valley, others reforming off the coast. And obviously there's a definite maximum here. Just off of New England, you can see the 40-70 benchmark, as we call it, is right here. And that was kind of used as a reference point to determine which storms we were going to keep in the database and which ones we were going to kind of ignore based on a certain radius around that point. So just to show some of where we are now, we're in the initial stages of kind of looking at some of the verification. And this chart's a little confusing, but I'll explain it a little bit. Any of the plots up here mean there's a left of track bias and a fast bias. Up here is a right of track bias, means it'll be moving offshore and faster. Then you have left and a slow bias, right and slow bias. So 24 hours ahead of time, you can see that there is a little bit of a left bias in the model and a little bit of a slow bias. So you can see more of the cases were clustered in this area. As we go out to 48 hours, so 2 days, it's not quite as pronounced actually. You can still see a little bit of a left bias here and a little bit of a slow bias, but there's definitely more spread. It's not something that's completely evident. And in 72 hours, this is the 3-day forecast. Obviously a lot more spread in each dot here. But you can still see a little bit of a left and fast bias and maybe a little bit of a kind of a slower bias here as shown there, but definitely a lot more spread. So far what we've determined, and this has only been studied over about a couple of years, does it hold merit? Well, there's no clear signal saying there is that right of track bias. But on average, the cases exhibit a slower bias and a left bias, actually, not so much what we call a right bias in the 2 to 3 hour time frame. But it seems we do see that bias where it's more offshore and then trends closer to the coast with storm systems in what we call the southern stream, or in the subtropical jet streams. Think of storms coming out of the Gulf of Mexico, for example, as opposed to coming across the Great Lakes and reforming off the Carolinas. So it's those southern track storms that seem to have more of that bias than what we call our northern stream storms. So we are continuing to do research on this, and we're going to add more cases from the past winter. So stay tuned for more on that. And I think, Andrew, you're going to lead us with the ocean effect snow, so I'll hand that to you.
Excellent. Thank you, Joe. Yeah, so this is sort of this ocean effect snow project is actually sort of a really recent project that a few of the forecasts in the office sort of taken on. I'm one of them. And sort of the goal of this project is to improve detection and communication of ocean effect snow events. And sort of what we mean by that is ocean effect snow. Basically, it's these snow bands that sort of are really localized and affect sort of especially coastal Massachusetts, especially Cape Cod, but also parts of the South and North Shore as well. And it's, in general, ocean effect snow events are not sort of well forecast by forecast model guidance. And the other challenge that we have with these events is that the radar beam from our office can actually basically it overshoots the snow bands themselves, because they're so shallow features that the further away you go from a radar, the higher up in the sky that you're looking. So that sort of overshoot can make these sort of snow events really difficult to really detect sort of in real time. And what kind of effects do these have? Well, obviously, it can disrupt travel on Cape Cod and the islands due to snow-covered roads, especially Route 6 on Cape Cod, and also just leads to poor visibility as we see with any sort of snow event as well. So this is sort of an area of newer research that we're sort of just getting underway with, but more to come with that. And what I'll do from now is I'll pass it back to Joe, and Joe will talk a little more about coastal modeling of what's called total water level.
All right, thanks, Andrew. And we'll probably have more on the ocean effect snow study in the coming months as we gather more data. We're in the process of doing that now. But also kind of on what we call the wet side of the house, we're doing modeling of total water level. And this is a collaborative study with an organization called the Center for Coastal Studies out in Provincetown, Massachusetts on Cape Cod. And we'll explain kind of what we're doing with them. On our side of the house, we've gone, if you've noticed, if you live near the coast, we've kind of gone graphical with our coastal inundation forecasts, what are also called total water level forecasts. We have a new coastal hazards web portal on our webpage, weather.gov/box/coastal, and that contains reference inundation maps and also wave run-up forecasts for some selected locations. So we're not just producing the traditional text forecast where we show for example, maybe Situate is expecting a 2-foot storm surge at high tide. Now we're able to show it graphically, visually through inundation maps. So that's one part of the study here. That's kind of what our office is providing. Now, on the other side, the Center for Coastal Studies is undergoing a project called Stormtype Pathways. And these are essentially areas where water connects from the coastline. So due to their elevation, they provide a direct connection between the shore or beach and the low-lying inland areas. So think of low spots, roads, walkways, areas near seawalls, in particular barrier beaches, maybe dunes. So once they're identified and essentially the elevations are recorded through LIDAR and other means, then protective measures can be taken to mitigate the effects of coastal flooding. Now, this is being done in Provincetown, and what we're looking at is actually a simulation from the model that is being used. So this is looking over the area from Provincetown Harbor, if you're familiar with it, on Cape Cod. And you can see as I click here, the water, you start to see some inundation based upon different water elevations. So the blue are the low spots. And obviously, you're not seeing a connection here with the coastline, but there's potentially areas of inundation. That's just because they're low elevation. But we have to go forward a little bit until you kind of see a connection start to go. Now you're seeing water on the beach, and you can kind of see right about here. There's one spot, there's potentially another spot here where these are going to link up. And once they link up, then this whole area in the back is low enough in elevation that it's going to become inundated. So if we can block the inundation at this storm tide pathway, then we can prevent inundation in this whole area of downtown Provincetown. And that's kind of what's been done. So this just shows kind of the elevation going along this transect here. You can see from the water, there is a little bit of an elevation, which is marked about here, and then it certainly just sinks right down. So once the water gets past this high spot, it's game on for flooding across downtown Provincetown. And as I go forward there, you can see there's the spot on the harbor, and then the yellow spot would be inundated beyond this storm tide pathway. And then further down, there's right in the downtown area on Commercial Street, and this dot, then there'd be more inundation through that shaded area there. So it just kind of shows that if we block these two pathways, then we can prevent flooding across much of the area. And that's a flower pot just noting Commercial Street in Provincetown, which I'll show in a minute. But this is now looking the opposite way, looking offshore. So what we're looking at, these are the spots that I was just showing on that inundation map. So what's been done in Provincetown is they've taken this information and actually built up some low spots on the beach. So this buildup protects a parking lot and some of a roadway. This area here, this is the pathway that protects downtown where that flower pot is. And then when there's a significant storm coming, a good example of that was the January 4th, 2018, the bomb cyclone or blizzard. They actually do some additional sandbagging here to protect the area from more significant flooding. But it's by running these, developing these storm tide pathways that we can identify these spots, and then we can also put this information on our coastal flood portal for everybody to see. So this is an example of our coastal flood mapping portal showing some of the areas of potential inundation, and you can go by high tide cycle, you can go by strictly by elevation, and actually identify some of these storm tide pathway locations. So this is done now, completed on all of Cape Cod. We'll be updating our inundation maps to show that. Also around Hull and Cohasset, Massachusetts on the South Shore has been completed. And the next phase of the project is to expand to Martha's Vineyard. So that is going to be done over the next couple of years. We've also completed the work on Nantucket. So that will be coming to this web portal soon. We also do quite a bit of university research collaboration, as I mentioned at the start. And in particular, these universities listed here, we've done some recent work with. In particular, University of Connecticut, we are actually applying for some Seastar grant research to develop what's called probabilistic wind forecasts, meaning probabilities of wind speeds reaching various thresholds, which could be used for things like tropical storms, hurricanes, or even typical nor'easters. University of Massachusetts, we've done a bit with University of UMass Boston, in particular here in the middle. This is a tide gauge. It's a radar-based tide gauge that's completely above the water. This is actually installed in Scituate, at Scituate Harbor. And it's a low-cost gauge. The total cost is about $15,000, which, believe me, is low cost. A traditional tide gauge that's submerged in the water usually runs about six figures, on the order of $150,000 to $200,000. So this is much more economical. There's no moving parts. It's completely powered by solar and transmits by cell phone. And there's no erosion from the salt water, so it's long lasting, and the maintenance is minimal every year. So UMass Boston has a research department that actually can produce these. There's also one in Gloucester, Massachusetts, and they maintain them for us, which is great. UMass Dartmouth, I'll get to in a minute. They've helped us with icing forecast, freezing spray, and also with total water level. MIT, we've done some work on climate in particular, looking at climate studies. University of Rhode Island with hurricanes. They're actually pretty well known for their work with hurricane strengthening in particular. So they work with the National Hurricane Center as well. And this one on the right is from Wheaton College, right next door to us in Norton. And several years ago, we actually had a project where we recruited a bunch of math majors to correlate the activity between rip currents at south coastal beaches. So think Horseneck Beach, first and second beaches in Rhode Island, and buoy wind direction and swell height. So they actually came up with a correlation. And in fact, we still use that today in our forecast software. It actually will take the buoy wave height, the swell information, and the wind direction and wind speed, and correlate, help us produce rip current forecasts for our beaches. So if you've ever used our surf zone forecast before you go to the beach, that's courtesy of Wheaton College. So a little known fact. I'm not sure if Rob and Andrew knew that because they're relatively new to our office, but that was done in the mid-2000s, actually, when we were in Taunton. So I'll just go through UMass Dartmouth in particular. We have done quite a bit of work with on the modeling front. They have a model called the FVCOM model that they run, and it gives us a bunch of different outputs that we use throughout the year. One is called vessel icing, which an example of that is shown here. It shows the potential for essentially freezing spray, which can lead to vessel icing in the winter, and it does all of the North Atlantic, really, from the Maritimes back across southern New England to Long Island. Also, they provide us with data for storm surge or inundation during our coastal storms, wave height, and some other parameters too. We're able to pull them right into our computer systems at the office. So just a little background on freezing spray. You may be familiar with this, but as ice builds on a vessel as shown here, its ability to right itself will decrease. So if it's in heavy seas, it makes it difficult to kind of maintain a forward motion. And if too much weight is added, the factors that right the boat aren't as strong, and it can actually cause the vessel to capsize, roll right over. And each new layer of ice that builds upon the vessel creates more surface area for the next layer, and that exponentially increases the weight. So that's definitely a significant hazard. And in fact, the Lady of Grace, which is a fishing vessel, I believe out of New Bedford, capsized in Nantucket Sound back in January of 2007 due to vessel icing. And today, fishing vessels from New Bedford and other ports, and certainly from Canada, frequently travel well offshore to George's Bank, shown here, for days at a time. So having these, 2 or 3 day heads up of significant freezing spray, significant icing, is really vital to the safety of them and their crews. So some of the other model output that we get, as I mentioned, things like wave height. These are run pretty much for when we have significant storms on the horizon. So not every day, but you can see some examples here of wave height forecasts back from this December 17th storm, which was actually a nice little snow producer the week before Christmas. There's also output, station by station. So this is looking at the buoy off of Boston Harbor, things like wind, direction, and speed, the height of the seas, and other parameters. And then also, as I mentioned, inundation. So here we're looking at Scituate, and it shows potential things like wave height, inundation across Scituate Harbor. So we have this information that we can incorporate into our forecasts at the office. It's just another tool we have to provide kind of the best forecast data that we can for our marine forecast program. Now, kind of flipping the coin here, one of the things that were underway this year, and we started last year, is called urban heat island mapping. And this really, on our end, we're just providing a heads up of days when temperatures are going to be 90 degrees or higher. And the volunteers actually will then go out and provide temperature measurements in their study area. And you can see for this coming summer, there's quite a few different stations across the country, mostly urban areas, throughout the U.S., East Coast, the Gulf, and even on the West Coast. In our area, the focus this year will be on the Mystic River watershed, so the communities listed there, including Boston, will be in the study. And the data is going to be used for resiliency planning. Think of climate change impacts, things like that, where these communities want to spend their money to help mitigate the effects of the urban heat islands. So it's really kind of a three-way thing here. It's the center of it is a field campaign where they're gathering the data. We have community engagement through volunteers. And then that will also lead to as I mentioned, the climate resiliency planning for all of these communities, kind of helping them focus where they want to, spend their money, because the funds for these can be limited, but for each community. So just an example here from last year. This was the city of Boston in 2019. an example, July 29th and 30th, we had volunteers look through 10 study areas in Boston, Cambridge, and Brookline. Some of their data is listed here, and that's all used as part of this whole study. So they'll be looking again, essentially days of 90 degrees or higher, and look at the different temperature differentials across the region. So that's a look at our research at the office. We're going to pause here, answer your questions. I'll bring Rob and Andrew back in, and then we'll go ahead. Andrew's going to go ahead and give us a weather briefing in a few minutes. But we'll start. Let's go through if you have any questions and comments. And again, you can feel free to use the chat box to answer yours. So let's see, from John. Here's a question about the tornado detection scale. How is it applied in real time? Is there an algorithm or calculated manually? Since I was involved in that study, I can help answer that, John. It was, it's actually just manually, kind of on the fly. You're eyeballing the values. So we look at the rotation on the radar. We know the environment. So we just quickly can kind of pile up the numbers together in our head. You know, do you have a 6, 7, 8, 9? And that will help you kind of just on the fly do that. You know, down the road, I probably can enlist the help of Rob here to do this, you know, detect it automatically. But it's easier, you know, instead of having to punch a bunch of numbers in, just kind of off the top of your head, we have the chart next to us, and we can just go kind of on the fly and figure out, you know, what our values are. On flash flooding, maybe I'll hand this one over to Rob since you discussed that. When it comes to predicting flash flooding, how do you determine when the ground is saturated? Is that measured directly or estimated?
So that's a great question. We do have soil moisture parameters that we can look at, but for example, the flash flood guidance that I had mentioned, that actually incorporates soil moisture, which is something that the River Forecast Center will consider, and also, you know, that unit stream flow flash product I had mentioned. Once you start to see increasing values of that, that's another indicator that the ground is saturated because you know, it's not absorbing as much of the rainfall, and you're starting to see a lot more runoff. So there's a few ways, but usually we have a general idea of what we call the antecedent conditions are, or the preconditioning. So we know well ahead of time, you know, that if the ground is very saturated, you know, the impacts of 2 inches of rain might be more impactful than, you know, if the ground was dry.
All right, thanks, Rob. And John's got a couple more questions. We'll go through, and we have I see a few more popping in. So what kind of software package are we using for data analysis for these projects? I know for the ones I'm involved in, which like the ocean effects study that Andrew mentioned, the tornado study, a lot of times we're just using spreadsheets to look through some of the things and calculate averages and means, things like that. Rob, Andrew, I don't know if you're the ones you're involved in, if you're doing anything different. It kind of is up to the folks involved. I'll let you guys answer that.
Yeah, so I've found, especially with big data, that the Python programming language can be very helpful. They have a package called Pandas, which allows you to do a lot of really great things with spreadsheets, including some of the stuff Joe just mentioned, like you know, means, maxes. The Pandas is basically like a Python module that's Excel on steroids, and very quick and convenient. So that's what I use a lot when I'm doing spreadsheet analysis.
All right, Andrew, did you have any comment on that?
No, I don't have any specific ones from what you all had shared. So
yeah, that's fine. That's why I leave it to smart guys like Rob. They're the programmers in the office. All right. And let's see, another one from John. Can freezing ocean spray be detected via radar, satellite, or other means? Typically, there's two ways, John. One is through our buoys, the coastal buoys. Many of them have sensors that can detect freezing spray, so you can actually see it reported on there. And another way is real time. We have the ferries that are out over the water, the Coast Guard. They occasionally report it to us, but that's about it. It's normally too light and too shallow to be detected by the radar. Satellite really can't capture it. It's fairly thin in appearance. So it's really just these real-time reports, buoys and vessels that are out on the water who will help us out. And in fact, in the future, there's actually a new citizen science program I'm hoping will be debuting in the next year or so. Commercial fishermen will actually have weather stations attached to their vessels that will report weather conditions kind of automatically. They don't have to worry about calling us or anything like that. It'll just be transmitted directly. So that's been used successfully down in the Carolinas, and that'll be expanding up here to New England in the next year or two. So we're looking forward to that. Question from Gabriel. Is the NWS still working on getting dangerous severe thunderstorm warnings to activate the WEA system, or the wireless emergency alerts? I guess I can take that, guys. Yes, we are. And guys, correct me if I'm wrong. I think it was pushed back to July sometime this summer. But what's going to happen is there won't be any cell phone alert for a storm that has the typical 60-mile-an-hour wind, quarter-size hail, thinking, the low-end severe storms. It'll be for the more significant ones. So once you get winds in excess of 70, hail in excess of, say golf ball size, really the more higher-end severe storms will be activated for that. Similar to what Rob mentioned for the flash flood warnings. You're not going to get the cell phone alert for every single flash flood warning like you do now. The base ones will not activate, but the considerable and the catastrophic will. So it'll be similar to that, Gabriel. And I think that comes later this summer. I don't know, Andrew or Rob, I remember seeing something on that in like the past week or two. I know it was delayed, so I believe it's the end of July, but don't hold me to that. I'm not sure, guys, if you know.
Yeah, I think it's mid-July.
Okay. Yeah, and we'll have an announcement, Gabriel, probably either on our website at the top on a link, or certainly social media. So stay tuned for that. Hopefully we'll have that this summer. Let's see, on our tornado study, and I believe, let's see, Rob, that was you, from Mackenzie. Are there any tools to detect tornado intensification over the span of years?
Over a span of years, I mean, I haven't seen anything like that. But I guess the simplest tool would just be okay. So I think is the question similar to what we had for the flash flooding with the ARI? Is that?
Yeah,
that's kind of.
You know what? That's what it's. Yeah, I think so. Like, in other words, and Mackenzie, correct us if we're wrong. I think it has to do with
like
detecting
average return
going from a weak tornado to a stronger one, something like that. Yes, that's what Mackenzie's asking.
Oh, okay. No, we don't have any tools like that. That would be something interesting to put together, especially for southern New England, where we typically have tornadoes on the weaker side. We're not often getting those EF3 or EF4 tornadoes like from the Midwest. So that would be interesting, but we don't have a tornado ARI tool, so to speak.
Right. Yeah. And the only thing we really have is the radar and kind of what we're seeing on there. So we might see the intensification, all of a sudden really gets stronger, and what we call tight and bright, where you have the outbound versus the inbound. So it's almost we're almost, I guess, kind of in the reactionary mode where we see things getting worse and we know it's intensifying, but there's nothing really automated as of yet. And I'm
Right.
guessing, guys, that's probably something that the National Severe Storms Lab is working on as part of their research right now. So I know that's probably in the books. So that is probably like a 3 to 5 year, project at this point, where we'll see the results of that. Great question. Yeah, go ahead, Rob.
Yeah, sorry. Additionally, I wanted to add too, I know that there's research out there that has shown tornadoes can be followed by like a lightning jump. So the new GOES satellite imagery has lightning detection, and I know that there has been some studies that show when the lightning detection has a big spike or a big jump, there is a little bit of a correlation to that storm maybe producing a tornado afterwards. So as far as intensifying and maybe turning into a tornado, that is another thing that we can look for.
Right. And Mackenzie, another source you could look at is you can just do an online search. It's called Warn on Forecast, and that's through the National Severe Storms Lab. That's what's being worked on nationally right now, where they're actually going to provide warnings based upon like a high resolution model forecast. So instead of us the eventual plan is, instead of us issuing these polygons like we do today, and then we cancel part of it, and as the storm moves through, the polygon will actually move along with the storm itself. So we won't have to sit there, draw these polygons, warn around the storm, and send the warning out. It'll actually be largely automated. So if you're interested in severe weather, or anybody else is too, take a look at, just do an online search of Warn on Forecast, and that's through the National Severe Storms Lab. That's an interesting project. So that's what we're going to be having, I would say, in the next 3 to 5 year time frame. We'll be starting to integrate that into our offices, but that might have something, where they're actually talking about tornado intensification based upon these very high resolution model forecasts, higher than the resolution we're dealing with today. These are like on the storm scale, think just a few miles, as opposed to like tens or hundreds of miles. So great question, and definitely something you might want to check out. So, all right.